In section 9.1, our aim is to understand the molecular and mass information given in a balanced equation. So we've looked at how to diagram a balanced equation before and what all of the different parts mean, but we didn't go into a lot of detail about what those coefficients can actually represent. So if I'm asking you to write the equation, 1 molecule of propane reacts with 5 molecules of oxygen to give 3 molecules of carbon dioxide and 4 molecules of water, you'd probably start by writing the compounds given. So we know we have propane, C3H8. We know we have oxygen. We know oxygen is one of our diatomics, so we know that's going to be O2. And we know that gives us CO2 and H2O. But now we have these molecule pieces in here that we have to represent. So that tells us how many of each of these molecules are reacting in this specific balanced equation. So that means we have 1 molecule of propane, 5 molecules of oxygen, 3 molecules of carbon dioxide, and 4 molecules of water. So remember in chapter 8, we learned about the mole and how the mole represented a quantity that we could use to discuss something. And that quantity is 6.022 times 10 to the 23rd. Atoms, molecules, whatevers that we're talking about. So we could say that 1 mole of C3H8 molecules reacts with 5 moles of O2 molecules to produce 3 moles of CO2 plus 4 moles of H2O molecules. So, in other words, these coefficients represent moles. Do they represent mass? So can we say 1 gram of C3H8 reacts with 5 grams of O2 to produce 3 grams of CO2 and 4 grams of H2O? We cannot say this, and we can't say this because we know that each compound has a different molar mass. So looking at O2, for example, we know that the molar mass of O2 is 32 grams per mole. Each oxygen is 16, and if we have 2 of them, that gives us a total of 32. We know water. We know that hydrogen is 1.01 times 2, and oxygen is 16 times 1, and this gives us a total of 18.02. So we can see that these do not work in terms of the ratio that's given in this equation if we're talking about mass. If I have 5 O2s, that is not equivalent of 4 H2Os, and that is because these compounds have different molar masses. So again, these coefficients represent the number of molecules or the number of moles of molecules because that represents a quantity. Mass does not represent a quantity of something. So we cannot be talking about these coefficients in terms of mass. For section 9.2, our aim is to learn to use a balanced equation to determine relationships between moles of reactants and moles of products. So in other words, we're now using these coefficients as a ratio to be able to convert between one compound and another. So we see this word stoichiometry. Stoichiometry is the relationship through coefficients of reactants and other reactants. So in other words, we can say how much reactant is going to react with something else based on the coefficients in the balanced equation. Reactants and products. So I could say X amount of product is going to be produced based on the amount of reactant that I started with. Or I can say, if I want to produce a certain amount of product, how much reactant will I need? Products and other products. So you could look at a balanced equation and say, if 10 grams of one product is produced, how much of the other product will be produced? Stoichiometry is a really powerful concept because it allows you to predict how much reactant is needed or how much product is formed. So stoichiometry lets you do quite a lot with just one balanced equation. And we do this through what's known as a molar ratio. So if I keep talking about a molar ratio, I'm talking about using those coefficients to be able to convert between one thing and another. I'm asking you to use the ratio of the coefficient in front of one compound to the coefficient in front of another compound to be able to convert. So in any given balanced equation, we have a number of conversion factors as long as we've been able to balance that equation properly. So again, remember the mole ratio comes from the coefficients, those numbers in front of each molecule. So again, I'm asking you to write the equation. Water decomposes to produce hydrogen and oxygen. So we know water is H2O. We know when we see a decomposition reaction or the word decomposes that we have one reactant and multiple products. So decomposes to produce means I draw my arrow. We know hydrogen and oxygen are both diatomic. So when I see these, I'm going to see them both as 2. Now we want to make sure we balance this equation. 2H2O and 2H2, and then we have to include states as well. So this is now a complete balanced equation. So a common question from this type of problem or using this type of reaction might be how many moles of oxygen will be produced by the decomposition of 5.8 moles of water. So what you would want to do here is follow the same process we've been doing through different types of dimensional analysis problems. You have a given piece of information, and that's 5.8 moles of water. So that's what you're going to write down first. You draw your line, as always, and that line reminds you something needs to go on the bottom and something needs to go on the top. It reminds you that you're looking for a conversion factor. So on the bottom, you're going to put moles of H2O, and this is why you don't want to rush to putting 1 mole of H2O on the bottom, because what we're going to do is convert to moles of O2. We can do this as long as we have a balanced equation that relates the two compounds to each other. And then what we do is we look for their coefficients. And those are the numbers that go in my conversion factor in my dimensional analysis problem. So notice I have a 2 in front of H2O. So that comes down in front of moles of H2O. And then there's nothing here, but there's an implied 1 in front of O2. So that goes in front of O2. Now, how many moles of oxygen? So I'm looking to calculate moles of oxygen. I can see I've reached moles of oxygen, so I can put my equal sign. And now I can do my calculation the same way I would any dimensional analysis problem. Take what's on the top, divide it by what's on the bottom. So in this case, I'm looking at 5.8 divided by 2, and that gives me 2.9 moles of O2. So we're just using the coefficients in a balanced equation as a conversion factor to be able to convert from one compound to another. In this problem, this is the same equation that we looked at in the beginning. You're asked to calculate the number of moles of oxygen required to react exactly with 4.30 moles of propane. So a lot of people will see this and they don't know what the words react exactly mean. It just means according to the balanced equation. That's it. So it means you're taking those coefficients in the balanced equation and converting using those ratios. So we start this the same way we would any problem with the given piece of information. So our given piece of information is 4.3 moles of propane. We're going to draw our line. On the bottom, you're going to put moles of propane. On the top, you're going to put moles of O2. Notice you were asked to calculate moles of oxygen. Because I have moles of oxygen and moles of propane in the same balanced equation, I can use their coefficients to convert from one to another. Now I'm just looking for the numbers that come in front of those compounds. The number in front of C3H8 is 1, so even though there's nothing there, it's still an implied 1. And the number in front of moles of O2, or in front of O2, is 5. The math is set up in a way that we know how to put this into our calculator because we're just multiplying across the top. 4.3 moles of C3H8 times 5 moles of O2 gives us 21.5 moles of O2. So this is the amount of oxygen in terms of moles required to react exactly with 4.3 moles of propane. So we are just using those coefficients as a ratio to be able to convert from one compound to another. In another problem, We're asked to calculate the number of moles of carbon dioxide formed. So here we are able to determine how much carbon dioxide is formed. But here we have two given pieces of information. We have 4.3 moles of propane and we have 21.5 moles of oxygen. So there's a couple of ways we could approach this problem. We can start first with 4.30 moles of propane, go through the same process that we've gone through before. We know we can convert moles of propane to moles of carbon dioxide because they're in the same balanced equation. We take their coefficients and use those coefficients as the number of moles in our conversion factor. The number in front of C3H8 is 1. The number in front of moles of O2 is 3. We do the math. We get 12.9 moles of CO2. Now, we want to know what happens when 21.5 moles of oxygen reacts. So we can go through this same process again. 21.5 moles of O2, and then we have moles of O2 on the bottom, moles of CO2 on the top. Looking at their coefficients, we know they're in the same balanced equation. The number in front of moles of O2 is 5. The number in front of moles of CO2 is 3. So people always usually ask, where do these numbers come from? The 5 comes from here. It's the coefficient in front of that compound in the balanced equation. The 3 comes from right here. Again, the coefficient in front of that compound in the balanced equation. And then when we do this math, we're going to multiply across the top first and then divide by what's on the bottom. So we have 21.5 times 3 and then divided by 5. And this gives us 12.9 moles of O2. You can see here, we've produced the same amount. And why have we produced the same amount? What we see here is in the previous slide, we had already determined that 4.3 moles of propane equals 21.5 moles of O2. That's exactly what we saw right here. Because 4.3 moles of propane equals 21.5 moles of O2, they are going to produce the same amount of CO2. They are stoichiometrically equivalent.